Now, I call this day oscillators in real life. Up until now, our pendulums have been point masses, and there hasn't been any energy loss in our systems, and we've been working with these various idealizations. And today we're going to look at, well, situations that don't match up to those idealizations. So now, let's say we have what we call a physical pendulum, which is an actual object that's connected to a pivot. You know, it might be a rod swinging back and forth, or it could be a disc or a sphere. It doesn't matter what the object is, but we're not dealing with a point mass. We will only deal with uniform shapes that you'll be given moments of inertia for, or that you might have to calculate a moment of inertia for. Either way. So the only force, the only force that causes torque in this situation, just like the simple pendulum, the only force is gravitational force. So Newton's second law says net torque equals I alpha. Our net torque is mg, and we said that the pivot is the distance d from the center of mass. So the net torque is mgd sine theta, and it's going to point back toward equilibrium, so it's negative. So this looks a lot like our pendulum did when it was a simple pendulum, only now the distance is d instead of being L. But now our moment of inertia is not. We don't know what it is. It could be any old object, so just leave moment of inertia as I, and alpha then still is d squared theta dt squared. And again, apply the small angle approximation, and that gives us minus mgd. I'll move this I to the other side, and sine theta becomes just theta. And following our pattern of simple harmonic motion, this coefficient here is equal to negative omega squared. So for a physical pendulum, then omega is square root of mgd over I. So if our object is not a point mass, then the angular frequency is root mgd over I, and by extension, therefore, the period is going to be 2 pi root I over mgd. And remember, as we said at the beginning, the d is the distance from the pivot to the object's center of mass. It is not the length of the object, distance from the object to the center of mass, because the center of mass is the point of application of the gravitational force. So if I wanted to find the period of a rod of mass m and length L for small oscillations around a pivot that at one end of the rod, we've got our rod. This is our pivot. I should have said a uniform rod. Yes. So then, well, our period is just 2 pi root moment of inertia over mgd. 2 pi root rod with axis through the end has moment of inertia 1/3 ml squared, which, depending on the problem in the AP Physics exam, you might be given, or you might actually have to derive using the formula. Moment of inertia equals integral of r squared dm. You might also be given the moment of inertia through the center is 1/12 ml squared, in which case you could then use the parallel axis theorem. And it's mass, g, and this distance then, it's going to be halfway down, so that is then L over 2. And we can cancel out a factor of L, we can cancel out a mass, leaving us with 2 pi root. What do we have? This 2 flips up to the numerator, joins the L. 3 drops down to the denominator. So root 2L over 3G, which is good. You should always check at the end for your units. We know the period of a simple pendulum is 2 pi root L over G, so this has the same units of seconds. So that makes sense. So that's how we deal with a physical pendulum. Another physical system is what's called a torsional pendulum, or a twisty pendulum. So what happens here is you've got an object hanging on a string or a wire or something, and then when it twists, there is a restorative force that is proportional to angular displacement Your book uses the Greek letter kappa for the constant of proportionality. On one of the old AP exam questions, I saw beta, the Greek letter beta. It doesn't matter. They'll tell you what the constant is. So again, we can say net torque equals I alpha. And if the torque is proportional to angular displacement and it's restorative, then we can say net torque is minus kappa theta, and that's equal to I alpha, which is d squared theta dt squared. Now, notice here, this isn't a sine theta, so there is no small angle restriction for a torsional pendulum. So that's kind of handy. What are the units of kappa here? That's a little bit confusing. Well, this is a moment of inertia times an angular acceleration. Well, actually, let's just think about the torque. So the torque is equal to kappa times theta, right, or negative. Torque has units of Newton meters. Theta has units of radians, which are dimensionless, so that means kappa also has units of Newton meters. Anyway, so then following our pattern, we got minus kappa over I theta equals d squared theta dt squared. And as always, when we have this pattern, this is negative square root of angular frequency. So the angular frequency, square root kappa over I. So for a torsional pendulum, a twisty pendulum, the angular frequency is root kappa over I, period, then is 2 pi root I over kappa. So you can use that to figure out what's going on with the system. I'd have to double check to be sure, but I don't think this formula is on the formula sheet, which means that you need to know how to write this equation and get it, or I guess you could memorize it as well. But I don't think that formula is given to you. But there have been questions about torsional pendulums on past AP exams. So wire is torsion constant Newton meter per radian. Yeah, you can optionally throw in this radian, but radians are dimensionless, so you don't have to. 12 Newton meters per radian, and a uniform disc of mass 250 grams and radius 2.5 centimeters is hung from it with the wire attached to the center of the disc. So we've got our little disc, we've got a wire attached in the middle, so it's hanging and twisting around there. So what is its period of rotation? Well, we know period is 2 pi root I over kappa. Torsion constant means kappa, in case I didn't make that clear. So that's 2 pi root uniform disk. Moment of inertia is 1/2 mr squared over kappa is 12. So then we can calculate what that period is going to be. 2 pi root 0.5 times 0.25 times 0.025 squared divided by 12. So our period then is about 0.016 seconds. Pretty fast. It's going to twist back and forth quickly. Okay. So those are two examples of harmonic motion in real life situations that are a little bit different than the spring and pendulum we've been dealing with before.